All right, we're very happy to have Eric give lecture 3. Take it away.
Thanks, Tom. Great. So I've already thanked the organizers plenty, I'd say. So, but why not? Thank you again. Good. So we're halfway, and you all are about halfway through your last week. So let's bring it home. I just wanted to continue yesterday a little bit before starting on this new trajectory. So two things that are a little bit of a continuation. The first is short. So I told this story about how an n=4 is super Yang-Mills. There are these nice bootstrap results of different sorts, which reproduce things that were originally calculated in AdS and significantly extended them in the case of these half BPS 4-point functions. There's an analogous story for the 2-0 theory in 6 dimensions, very closely analogous actually, and those results are very nice, if not even nicer, in the sense that that's the M theory regime about which we'd like to know even more. And so there are three parts to this analogy, which I just want to mention briefly, and I can give references later. So first, in the 2-0 CFT, there again is some infinite tower of half BPS operators that survive in the large N theory. They comprise the single trace superconformal primary spectrum. And so if we label these by P, then there were some bulk calculations at tree level of these 4-point functions of 4 different half BPS operators. These were again reproduced from a bootstrap ansatz by Rastelli and Zhao, an ansatz that was later proven, just like in the n=4 case. So these were bootstrapped. There's a large C numerics match to the holographic anomalous dimensions for these double trace operators in the same sense that I described yesterday. For by match, I mean the boundary of some allowed region matched up to previous computations of anomalous dimensions of the double traces of these half BPS operators. And finally, and this is slightly away from the holographic setting, just like in n=4, where they proved numerically, or rather analytically, that any interacting n=4 SCFT of any kind must have central charge bounded below by 3/4, where 3/4 is that of the SU2 gauge theory. In the 2-0 case, they showed that for any interacting 2-0 theory, C is bounded below by 25. And 25 is exactly the central charge of the world volume theory of 2M5 branes. And so that is a very lovely result, because it's the kind of theory about which we know very little. It's well outside of the supergravity regime. But again, there's this match between what seems to be the landscape of such theories and the theories that we sort of already knew about, in this case, where our information really came even more strongly from gravity. Good. Okay. That's that. I'm happy to field any questions about that, but as I said, I'll provide references later. Okay. And so I said yesterday I wanted to give you two bootstrap, two points of contact between the bootstrap and computations of holographic correlators. And the first was the top-down one involving n=4 and this 2-0 extension that I'm talking about here. But a second was a sort of bottom-up connection. And so that one I will try to describe briefly. So we can reproduce the structure of Witten exchange diagrams from CFT. So what do I mean by that? So suppose we have an operator O, a scalar operator O, whose OPE with itself includes the identity. It's double trace composites. And we assume that there is some other single trace operator phi in there as well. And we can ask, given the presence of this phi, what does that imply about the full correlator 0000 as dictated by crossing. And this is the same question as asking, if I have a crossing symmetric set of weight and exchange diagrams, what is the conformal data? Here we're just setting this up in CFT and asking, can we determine that conformal data by crossing, assuming the existence of this single trace coupling? And indeed, you can show that the double trace data you get out is what you get from computing explicitly an exchange weight diagram. So pictorially, what we're asking is, if we have in the, say, T channel, so the external operators are always here, the exchange was some phi, then what does the sum in the S channel look like? What exactly are we summing over, and what are the OPE coefficients there? And we know the answer, and the answer is that it's these, with the OPE data dictated by an exchange diagram, possibly modulo some low spin ambiguities, which are understood as, the addition of contact interactions in the bulk, which can modify those. And there's an elegant method for answering this question. And that is to compute the crossing kernel of the conformal group. Okay, so what does that mean? So if we have some, let's call this phi prime. If we have some phi prime exchange in the T channel, we can write this formally as a sum over spins and an integral over dimensions. This is just some way of writing what appears in the S channel, weighted against some sum of operators phi, whose dimensions are delta and spins are j, times, just by definition, the overlap of this S channel exchange of phi with the T channel exchange of phi prime, divided by the norm of this conformal block. Right, so imagine for a moment that the conformal blocks form a complete basis for the decomposition of 4-point functions. Then this object here, right, this is just a statement that we're going to expand the T channel block in the S channel basis. And this thing underlined in green is just the branching coefficient. The conformal blocks are themselves not exactly a complete basis, but closely related objects, sometimes called conformal partial waves, are. And so with a couple sort of formal assumptions that are going into this, the object in green here, this overlap between S and T channel blocks divided by the norm, is capturing this OPE data for us. And this is what is, by definition, the crossing kernel. Tells me a block in one channel, how it decomposes into blocks in the other channel. It's the basis coefficient for that decomposition. And from now on, I'm going to just imagine this norm is 1. Okay, so that allows us to clean things up a little bit. Okay, so how can I envision this thing? Well, this thing is otherwise known as a 6J symbol. That may or may not be helpful. This is really the setting in which I first learned about 6J symbols, but imagine that we have our S channel block here with phi, and we're trying to compute the overlap of the T channel blocks. We want to glue them together. That's what taking this overlap means. So in the T channel, 2 and 3 fuse onto the operator phi. Okay, so we're sort of connecting these lines and connecting 1 and 4, and they fuse onto this operator phi prime. And just taking this and making it less ugly, you get a tetrahedron where the lines label operators according to the fusions in each channel. So I've just made this nice and twisted it around a little bit. Okay. So this is the definition of the crossing kernel. And given that we've written the decomposition as this integral over dimensions and sum over integer spins, the crossing kernel has poles at the locations of the operators that are exchanged when we do this cross-channel decomposition. So a pole in the crossing kernel will mean we imagine we can perform the contour of this delta integral and pick it up, that will give us an exchange in the S channel. So this thing has poles, and the question is, where are those poles? That will tell us the dimensions of the operators being exchanged, and the residues will contain the OPE coefficients. And in this case, with the external operators being identical, also the anomalous dimensions, because there will be double poles for those. So where are the poles? You can just compute this object, abstractly. It's just something which is determined by the conformal group and the dimensions of the 6 operators and the spins of the 6 operators participating in this. And you can just compute it and look at it. And so it has poles at the double trace twists, where I'm ready the twist is the dimension minus the spin. And the residues equal the OPE data. So it's a little simpler here if we imagine the external operators 1, 2, 3, 4 are not all the same. So if that's the case, then these are simple poles. And the residue of this thing at the twist of these double twist operators comprised of the external guys gives me the product of OP coefficients, which I'll just continue to call A, N, comma, L in accordance with yesterday's notation. In the case where you have some degeneracies, like an identical 4-point function, then you also have double poles. And the double poles give rise to the anomalous dimensions. How do we see that? Well, remember, we're integrating this against a block. And so if there's a double pole, then we'll get a derivative with respect to delta of a block. And that means that we're expanding the dimension of an operator being exchanged to first order, because the conformal blocks, if you recall, have some exponential dependence on dimensions, like e to the delta. Okay, so you might wonder what the 6J symbol actually looks like, mathematically as an object. And in even dimensions, it is a sum of products of 4F3 hypergeometric functions. And I think this can actually, in some cases, at least be massaged into a 7F6. No further comment about that. But that's what this is. Okay, so and the poles are poles in delta space, say for some fixed J, or in twist space more precisely. Okay, so that was what I wanted to say about that. So are there any questions about this kind of kinematical bootstrap reproduction of exchange diagrams before we move on to the space of holographic CFTs? Okay. Let's see here. All right, so we're going to talk for a little while about a paper by Heemskerk, Polchinski, Penedonis, and Sully, or rather Heemskerk, Penedonis, Polchinski, and Sully, to respect the alphabetical ordering, which was called Holography from Conformal Field Theory. And this came out in 2009. It by now is famous and is known as HPPS. And they were trying to understand what kinds of theories have nice bulk duals, where in the optimal circumstance, nice means a theory of Einstein gravity coupled to some small amount of matter of low spin. Ideally, one would like to construct a theory with just Einstein gravity and AdS. It's not known if that's actually consistent, whether you need other light matter, but stopping slightly short of that highly ambitious goal, they were concerned with just trying to show or discover necessary and sufficient conditions for the bulk dual to be semi-classical gravity to admit a local description with a controlled derivative approximation where higher derivative terms are suppressed by some uniform scale, which can be identified in CFT terms. And they made a conjecture to this effect. Which I mentioned in the first day, which is that, well, in order to have a semi-classical bulk description, we want large N or large C. And in order to make the spectrum look sufficiently sparse and effective field theory-like or Einstein gravity-like, we would like there not to be any higher spin fields. That is in part influenced by experience from string theory, where higher spin fields come in infinite towers, and the theory is immediately rendered non-local because of the infinite set of derivatives that come along in writing such an action. And so let me just say, remember, this is the dimension of the lightest single trace operator of spin j greater than 2. So these two conditions seem necessary, and their conjecture is that they are sufficient. So in other words, large N plus large higher spin gap, or large delta gap, imply a local AdS dual. This is how it is usually phrased. So you might think this feels quite natural. And it is natural that this would be a necessary condition. But what is adventurous about it is the claim that it might be sufficient, because all that is being imposed is a single spectral condition, aside from large N, of course. And the claim is that that takes care of everything. That all the OP coefficients, not only does the spectrum look the way you might want it to, but all the OP coefficients behave accordingly, and higher vertices behave accordingly, such that the bulk theory exhibits this form of locality, which is not guaranteed. And so in the past, I guess, by now 12 years, there have been various efforts to try to prove or substantiate this. And the punchline is that the conjecture is still standing and seems very likely to be true, and has sort of not been proven in the most rigorous sense, but I think most people believe it is true, and there's a lot of physics probably still to be understood, but that it's true. Okay, so that's my personal view, and that seems to be the personal view of many, but it's still an active area of research. And I think I'll talk about sort of what is outstanding and what questions related to this one might want to think about after I summarize what it is that they did. So what did they actually do? Well, they provided some indirect evidence for this conjecture. The evidence they provided is not really logically exactly what one would want. But here's what they did. They argued, really proved this statement, that there is a one-to-one map between the following two things in the bulk boundary. So in the bulk, AdS contact vertices in a scalar effective field theory on the one hand, and on the boundary, crossing symmetric solutions to generalized free scalar fields plus perturbations. And to be slightly more precise, they did this for 4-point functions. So when we talk about contact vertices, I mean 4-point contact vertices. And they're looking at crossing symmetric 4-point functions that perturb around generalized free fields. Okay. So in the bulk, let's talk about the bulk first. They look at a minimal scalar plus chordic corrections and no gravity. Okay. They make some comments about gravity, but they're really just stripping it down to the essence of a scalar model with interactions. And the fact that gravity is not included is part of what they did not actually manage to prove. And they didn't look at any 3-point functions because the model they're considering has no 3-point functions. Nevertheless, it was a very powerful thing that they showed. So they take a bulk action of the form d phi squared plus, let's say, g naught phi to the fourth plus g2 d phi to the fourth plus g3 d phi squared d squared phi squared plus dot dot dot. Here I've written the first several quartic terms you can write down that don't vanish upon using the equations of motion for a real scalar field phi. Okay. And I've ordered them in terms of the number of derivatives. And they computed the 4-point amplitude A corresponding to each of these solutions. As we said yesterday, these are just d functions in position space. So they're just noting that you have some quartic interaction in the bulk. Associated with this is an amplitude, a contact amplitude. It's automatically crossing symmetric by the holographic dictionary. And then they wanted to show that there exists crossing symmetric solutions on the CFT side independently, and that the number of solutions matches, first of all. And then moreover, that the structure of the solutions, say the OPE data extracted from both of these matches. Okay. And so the logic is that, just to try to be completely clear, the logic is that when you can show this kind of map, you're substantiating the idea that in this sort of very simple kind of model for a system with a large gap, any theory on the CFT side which solves the CFT axioms like unitarity and crossing has a bulk dual which looks highly local. So that's what they did in the bulk. They constructed these things, whose structure we talked about yesterday. And on the CFT side, they looked at solutions to crossing in order 1 over C with max spin L. So remember, if we look at solutions in order 1 over C, perturbations around generalized free fields will just involve double trace exchanges because there are no cubic couplings here by construction. And so this looks like a sum over all these double trace operators. There's first of all the OPE correction, A1. And then there is the generalized free field OPE times the anomalous dimension gamma 1 times a derivative with respect to n, acting on the conformal block Gn comma L, the exchange of the NL double trace state. So this is what solutions of this form look like. So on the CFT side, you say that this data has a 1 over C expansion, and I want to solve crossing for these. Right? And generalized free field theory gives me A0 here. So the A0s are known in closed form. In fact, they derived them in their paper. And they said about solving for A1 and gamma 1 upon imposing that the spin L is bounded above by a capital L. And in doing so, they showed that for a given capital L, the solution maps onto some vertex in the bulk, which has the same maximum spin that you would expect from the kind of argument I gave yesterday. Okay, so they match solutions, they match the counting of solutions. And so that was thorough and very enlightening. The story becomes somewhat, well, clarified at the very least in Mellon space, which I feel compelled to at least introduce briefly. Mellon space is an arena for computing CFT correlators that seems highly well suited to computing CFT correlators in large C theories, for reasons I will explain now. But there have been papers exploring the utility of Mellon amplitudes in non-perturbative CFTs, namely one from last year by Penedones, Silva, and Zhuboyedov called something like non-perturbative Mellon amplitudes. It is just an integral transform of the position space correlator, but the word just is kind of misleading because it really makes some features quite manifest. So we can write our correlator A as an integral transform with respect to two Mellon variables, S and T, with some measure. Let me write this like this. There are many different conventions in the literature. I'm sure you will notice them if you look around. Let me just write this for a moment. Of some measure times some melon amplitude n. Now, this u and v here, the u to the s over 2, v to the t over 2, those u and v are the cross ratios. And s and t are melon variables, which are a lot like Mandelstam variables, and you can think of them as a kind of Mandelstam variable fit for computing AdS amplitudes. Although here, really, this is just integral transform. You're free to think of this as something on the CFT side as well. There's a bunch of gamma functions, which are kind of here by convention. And then there's this thing m called the melon amplitude. And so we have A in position space, we have m in melon space. And so these integrals are contour integrals. The contours run along to one side of all the poles of the integrand. I won't be so explicit about this, but they are contour integrals in the complex S and T planes. Okay, and finally, this U here, this is like a Mandelstam U. I sort of tried to write it a little weirdly, so it looks different from the other one. It's not a cross ratio. This is equal to, so let me sort of write this like this, capital U equals minus S minus T plus 4 delta, where delta is the external operator dimension. So for a CFT with an AdS dual, or really any CFT with a discrete spectrum, M is a meromorphic function of S and T. Let's go over here, a little more room. There are two types of poles in this integrand with respect to the 1 over C expansion, at least. In other words, thinking about tree-level amplitudes in AdS, CFT correlators at order 1 over C, we already know what kinds of operator exchanges to expect, single traces and double traces. So first of all, M will contain single trace poles, and the poles are sitting at values of S and T, depending on what channel you're in, of the twist corresponding to the exchange of some operator of twist tau star. Okay. This has a pole at S equals tau star, say, for some S channel exchange of an operator of twist tau star. And so you see that there will be a contribution after you do the integral to the position space expansion in the S channel of u to the tau star over 2, which is indeed how an operator of twist tau star contributes to the U channel, the S channel conformal block decomposition. So poles very, very neatly reproduce what you know from the position space OPE limits. And the residues encode the OPE coefficients. Okay. On the other hand, the gamma functions encode the double trace poles. And that's clear just from their form. Because the external operators are all identical, the gamma functions appear squared. And so as a result, there are double poles. And that means that upon doing this integral, you will find anomalous dimensions that come with logs in the position space decomposition, and also corrections to OP coefficients, which come when the derivative doesn't hit the block, but it hits the rest. Okay. So the double trace poles are very explicitly encoded in these gamma functions, which are sort of pulled out from the definition of the melon amplitude. And so that allows us to think of the melon amplitude itself as just encoding the single trace data, and very neatly encodes this fact that the single trace data, by and large, determines the double trace data, right? Because when you evaluate the gamma functions on one of these double trace poles, well, it multiplies by m evaluated on that pole, and so that's going to be some number. And so if m itself is encoding the single trace poles, when you evaluate it on the twist of a double trace pole, you get some number which tells you that the residue is determined by the single trace exchange effectively. Okay, so why did I introduce this in the context of HPPS? Well, the melon amplitudes have single trace poles when there are single trace exchanges, but for a contact diagram, the melon amplitude is just a polynomial. There are no single trace poles. It just gives you a regular function of S and T. And in particular, we can just enumerate crossing symmetric polynomials in S and T, and we get exactly the amplitudes that this infinite series of contact diagrams would generate in the bulk. So these vertices give you crossing symmetric amplitudes. In null space, they are polynomials. But in null space, we could just write down all the polynomials. They're automatically crossing symmetric. And so it's clear there will be some correspondence if we just write them crossing symmetrically. Okay. So the point of doing null space here is just because the enumeration of solutions becomes much easier. The correspondence they're establishing was not originally done there, but it just is nicer to sort of work with on-shell quantities, so to speak, where in the bulk, instead of enumerating vertices, you enumerate amplitudes, but those are just manifestly the same types of null amplitudes you would get from the CFT side. Okay, so that was the gist of what they did, and it substantiated this more general conjecture. Let me pause and ask if there are any questions.
Can you explain again this thing about the maximum spin that you are imposing? So is capital L also, so as I understand what you're doing, what you're saying is that you take the exchange diagram with a single trace exchange and you decompose it into the double trace blocks. And capital L is the spin of the single trace operator. And
no,
as you said yesterday.
I didn't explain this very clearly. So in this game here, there are no single trace exchanges. Sorry, there are no single trace exchanges here. In explaining the structure of Mellon amplitudes, I think I might have inadvertently introduced some confusion. What is done is the following. So suppose we have some, okay, so good. We know that contact diagrams in the bulk correspond to polynomial Mellon amplitudes without single trace exchanges. So suppose we have some Mellon amplitude, which is just a constant. The spin associated to the solution is just read off from the degree of the polynomial. So when you write these solutions in ST and U, just like if you're doing scattering amplitudes in flat space, the spin is given by, say, expanding in small s and asking what is the maximum power of s that appears. That defines capital L for you here. So in the constant case, L equals 0. And this solution matches in the bulk to what you get from phi to the fourth theory, which has no derivatives of the vertex and turns on double trace data of spin 0 only. Okay, good. So now let's take this to be s squared plus t squared plus u squared. This guy has spin 2. And this is the solution you get by looking at a d phi to the fourth vertex in the bulk. In general, the Mellon amplitude, which is polynomial, will be some sum over powers of these symmetric polynomials in ST and U, where sigma 2 is s squared plus t squared plus u squared, and sigma 3 is STU. And so for each such solution, there is a bulk vertex for which that is the corresponding amplitude. And so just perhaps to give one more example, if I took b equals 1, a equals 0, so that I'm looking at the STU solution, that has spin 2, because u is constant minus s minus t. So if I define spin as the maximum power of s as I expand in small s, the number is 2. And the bulk vertex there is d phi squared, d squared phi squared. But this has spin 2 because you have 6 derivatives, but the derivatives are split such that because it's a real scalar, you only ever have spin 2 no matter what channel you decompose it to. On the other hand, d squared phi squared, or rather to the fourth, this would give spin 4, and that would correspond to, well, I guess sigma 2 squared. Okay. So is that clear?
Yes, thanks. Yes.
Great, thanks. I meant to go into some more detail actually, so thanks for your question. Any other questions? Okay, so what they didn't do was, first of all, include gravity. Second of all, show that it's Einstein gravity. And so what does this mean? Well, on the level of, say, correlation functions, recalling that the graviton is dual to the stress tensor, one would want to show that from these assumptions alone, the tree level, say, 4-point function of the stress tensor is equal to that which you get in Einstein gravity, plus, say, 1 over delta gap corrections for any n-point function of stress tensors. This has not been done, by the way, for all n. And in fact, even the 4-point function of stress tensors in Einstein gravity and AdS has not been explicitly derived in AdS 4 or greater.
But the 3-point vertex will also change the story, right?
Yes, absolutely. So that's the next thing I was going to write down. So, you know, this line here includes n equals 3. So in general, they did not talk about 3-point functions. And so the most universal one that any theory that looks like the kind of theory we're after would have would be TTT, the graviton 3-point function. And then one would like to show that the 4-point vertices are suppressed by this delta gap scale. In other words, that the derivative expansion in the bulk proceeds in powers of 1 over delta gap, because that's supposed to be the universal scale that suppresses all this non-local physics. So some of this, I mean, by and large, this has been done, certainly not the endpoint part, but the next major sort of step in this program was in attacking this. And so let's talk about this a little bit. There was a paper by Chems, that is Kamanho, Edelstein, Maldacena, and Juloyedov in 2014, I believe. And so they worked in the bulk. They did an AdS calculation. And they said, let us look at a theory of Einstein gravity corrected by higher derivatives. And here they're working in, well, let's just say AdS 5 or greater. AdS 4, there are some subtleties because the number of stress tensor 3-point vertices goes down by 1. In the bulk, that's due to the fact that the R² term is topological. Here, I've just written the first 3 terms in the expansion, and I've been cavalier about the index contractions because it doesn't matter. So what did they do? They did a bulk causality experiment. And they showed that alpha 2 and alpha 4 being non-zero violate causality in the absence of new physics at some scale by which these vertices are suppressed. So just schematically, what did they do? Well, they did an experiment where gravitons are traversing shock waves, and by tuning the polarizations of the gravitons, they showed that you can always engineer a causality violation in the bulk for some polarizations, no matter what the value of these couplings is. In their paper, the causality violation is discussed in terms of what's called a Shapiro time advance. So that's the idea that if you have some shockwave moving through the bulk, some pulse of energy, and you're a graviton and you're traveling across it, the energy sort of knocks you forward in time, not back. But there will always be some polarization, which knocks you back in time. And in terms of the crossing of the shockwave by the graviton, it's called a time advance because it looks like you gain time by crossing this shockwave. So the first conclusion was that these two vertices must be suppressed by some scale of new physics in order such that causality is restored by the inclusion of those, say, heavy particles. And they looked at the different ways to solve this problem. And they
Can I actually ask?
Yeah.
In that context, how does the inclusion of new physics at some scale corresponding to these couplings restore causality?
Yeah, so it's a little bit tricky in the sense that, so what they found is that higher spins can solve the problem. But importantly, there needs to be an infinite tower of higher spin particles. And if you look at the effect of any one, then it just makes the problem worse. They did not give a explicit and certainly not some unique mechanism by which this is evaded. They gave arguments for that if it is to be evaded, it is to be evaded by the inclusion of higher spin particles in an infinite tower. And of course, the example which is known is string theory. So that gives confidence that this can be done. And as usual, there's a question of whether there are other ways to do it besides what string theory tells us. Yeah. Good. And so an infinite tower of higher spin particles that appear at some heavy scale, like m higher spin, which would be dual to delta gap in the CFT, can fix this problem. And in particular, they showed that the expectation from dimensional analysis of this action suppresses these coefficients. So let me phrase this on the CFT side. The stress tensor 3-point function, which is dual to the graviton 3-point coupling times some kinematic vectors, is known to have 3 independent tensor structures. And we're free to parameterize them in terms of that which Einstein gravity gives us, and that which, including the r² term, gives us, and that which the r⁴ term gives us. Because there are just 3 independent structures, which is a function of the fact that the stress tensor has spin 2 and is symmetric and conserved, that's why they only had to look at these first, these first 3 gravitational couplings. Okay. So anything else beyond this, of course, an action can have those, but they will just tweak the coefficients of these second 2 structures. Okay. So sufficient for them to consider this. And so the conclusion is that alpha 2 is bounded above, or really of order of 1 over delta gap squared, and alpha 4 goes like 1 over delta gap to the 4th. So here they're making a step forward because first of all, they're considering 3-point functions. And second of all, the fact that it's a higher spin scale specifically is entering the argument. One thing that deserves to be mentioned here, and about which much fanfare was made, was that in 4 dimensions and 4 CFT dimensions, alpha 2 is known to be proportional to, proportional to at least the difference of A and C central charges divided by C, all absolute value. And so these central charges appear all over the place. They are fundamental constants of the CFT, really. And they appear in various holographic settings too. For example, in corrections to the eta/s entropy to viscosity bound. They appear in computations of superconformal indices, in asymptotic ranges of temperature. They control the asymptotics, and handfuls of other places. And so it's very interesting to see that this ratio is bounded by the higher spin gap. So that's one note about this. Another note is that this was subsequently proven in CFT by Ahami-Judi et al. And the argument sort of proceeded somewhat similarly to the bulk argument. They are using a form of boundary causality to prove this, but they find the same conclusion. You can also extend this type of argument to other 3-point functions. So for example, one property of the types of theories that we're after is not just that the gravitational sector looks like Einstein, but that it's isolated, which is to say it's gravity plus matter, and there are no couplings that are linear in the matter with a bunch of other gravitons. So is this thing suppressed here? Well, it would be if the expectation is that the bulk action is Einstein gravity plus the matter sector. A TTO coupling where O is, say, dual to phi would mean that there's some vertex like this, which is non-zero, but that would spoil the consistent truncation to Einstein gravity. And so what one wants to show is that this too is suppressed by some power of delta gap. And the expectation from the bulk is sort of taught to you by asking what is the first vertex that can give rise to such a 3-point function. And so that vertex is let's say the bulk is t plus 1 dimensional, a phi Weil squared coupling. Where here I've written in terms of Weil instead of Riemann so that variations of the spectrometric preserve the AdS solution. And this has 4 derivatives, so you'd expect that this 3-point function, if there's an analogy to be made with the causality violation in the TTT case, is suppressed by 2 powers of delta gap, and indeed that can be shown. And likewise for all sorts of other 3-point functions where there are high derivative vertices you can turn on in the bulk. So the correspondence that HPPS envisioned, where the higher spin gap is controlling the bulk effective field theory expansion, seemed to be correct after all these computations.
How does a dilaton fit into this last point?
Right. So I'm just imagining being an Einstein frame. That's the frame in which there should be a consistent truncation to Einstein gravity. So I think it fits fine. You just have to do that. Yeah. Any other questions? Okay. So more recent work, that would sort of bring you up to speed. Showed that the 4-point vertices are suppressed by the appropriate mass scale you'd expect in the bulk. This is this work that I referred to a couple times by now by Caron Huo et al. Involving these dispersive CFT sum rules and AdS versions of these flat space S matrix arguments that were made before. So that almost kind of seals the deal for this whole picture. Of course, formally one would like to show that the endpoint functions are those that we expect, say for the graviton. And also one would like to show that in the 4-point vertex case, it's the higher spin scale which is somehow suppressing these terms, whereas in that most recent paper, at least, this is not part of the analysis. It remains to be seen whether there is some interesting physics to be understood about the way the scalar sector of the theory couples to the rest. From the CFT point of view, scalars are sort of hard to constrain because they contribute to amplitudes in a way which is slower than particles with spin in the regimes where constraints can be found. So I think there is some interesting stuff to do, but I'm happy to discuss it, although in the interest of time, maybe I won't belabor that at the moment. Of course, if you have questions, please ask. One thing that would be nice to talk a little bit more about is, so we have this set of constraints here. And if you're interested in finding constraints in the CFT side, what are the tools? So one of the most important analytic constraints is that of boundedness of amplitudes in the Regge limit. There are some rigorous results on the CFT side here, which have been used to sort of constrain or rule out the space of holographic CFTs. I think, though, I won't discuss this too much, although I feel I should. So let me actually do that. Okay, so let me give a brief introduction to that. So you've probably heard of the chaos bound. This is a version of a Regge boundedness property of CFT correlators. And the Regge limit is a certain kinematic high energy limit of CFT correlators. So this here is a regime in Z and Z bar, which is Lorentzian. It's dual to high energy scattering in AdS at fixed impact parameter, where the impact parameter is like the distance at the point of closest approach between two particles flying through the bulk. And in terms of Mellin space, if you have some Mellin amplitude M, S, and T, M of S and T, then the Regge limit corresponds to large S and fixed T. Now, what is the bound? So in all CFTs, namely non-perturbatively, if I have some amplitude A and I study it in the Regge limit, then it can be parameterized as growing like Z to the 1 minus J naught, where, well, I guess I should actually do this in terms of the Mellin amplitude, having just stated it in that language. The amplitude would grow like S to the J naught. And so what is the bound? J naught is bounded above by 1 rigorously for any non-perturbative 4-point function in the CFT. So this is non-perturbative. In a planar CFT, this actually gets slightly weaker. So that is to say, if you look at a 4-point function at order 1 over C in a large C theory, then the bound becomes J naught less than or equal to 2. And this bound here is the same thing in slightly different language and slightly more generality as what was originally known as the chaos bound derived by Maldacena, Schenker, and Stanford. This turns out to be quite powerful because conformal block by conformal block, operators of higher and higher spin contribute more and more strongly. And so operators of spin greater than 2 have to be sort of rigidly tied together in order to satisfy this bound. And one kind of quick application of this, which I think we'll all be able to see together based on what I've said, is the following. If I have a local AdS theory, and I have some random contact interaction, d to the 20, phi to the 4th, this is not allowed. If I just have that term, it's not allowed because that grows like spin 40 in the Regge limit. And 40 is much greater than 2. So a local AdS theory cannot have a finite number of contact terms that are not in the following set. Phi to the fourth, which contributes like spin 0. It's just a constant, not null and amplitude. D phi to the fourth, which contributes like spin 2, which is allowed in the planar theory. And like we said before, d phi squared, d squared phi squared. So these three contact interactions can stand alone in a theory that satisfies the Rechet boundedness property. But anything higher than that would have to come as part of an infinite tower, and locality would be lost. So already the chaos bound, this Rechet bound, was a strong constraint on the types of actions that HTTPS were tinkering with. Showing the suppression of the coefficients is something else, and that's what was done more recently. But this already is sort of nice. It shows you that you can't just throw whatever you want into your bulk EFT. There are constraints. Okay, I'm glad I went into that. Hopefully that was clear. Are there any questions before we move on from that?
Can I ask a question?
Please.
This in this in the Regge limit, you said it's a fixed impact parameters limit, but isn't it true that impact parameter and T are in Fourier transform of each other?
And T, you said?
This S and T, the momentum transfer of and T variable and the so the momentum transfer and the impact parameter are Fourier transform of each other, right? So does fixed impact parameter implies fixed T in the Mandelstam variable?
Yes, yes. So you take large S and fix T, and so you get some growth, say S squared in the case of gravity, times some function of T. And then you can tune the impact parameter to be large or small, and in different regimes you see different types of physics. If you take the impact parameter to be large, then you're approaching, in AdS language, you're approaching the boundary and you're approaching the light cone regime. Taking it small is where you get stronger constraints, and well, as you well know, that's where some of the interesting physics is. But yes, that's the map between the parameters.
I have a question.
Mm-hmm.
So this chaos bound, I'm not sure if I'm correct about this, but I believe it was said that if the chaos bound is saturated, then this has something to do with a black hole being in the bulk. So how do you see this from this entire story?
So the way I've told it, you don't, there's no, indeed, I haven't mentioned black holes here. So the way to think about it is that whether the chaos bound is saturated in some correlator or not is really a property of a theory. And when we talk about the behavior of a correlator in this limit, we're talking about a perturbative amplitude in some kinematic regime. But that theory would also have black hole states. And the black holes in that theory would have certain properties, which, as you are suggesting, follow from the fact that the chaos bound is saturated. And they also have these properties of their perturbative amplitudes. So we can talk about one or the other. And yes, the chaos bound is relevant for different types of physics. But I tend to think of it as a property of a theory.
Okay, thank you.
Sure.
Sorry, just to clarify. Sorry.
Mm-hmm.
Yeah.
Mantra, I think you were first. Which is
Okay. Yeah. Sorry. Just to clarify, does the planar Rechet bound imply that in the CFT there is a higher spin gap? Or?
No, it does not. So if you look at theories with finite higher spin gap, they too must obey this bound. But what happens is that J0 is in general a function of the gap. And at finite gap, it would be strictly less than 2.
Okay.
When delta gap goes to infinity, J0 goes to 2. And so in general, J0 is some function of delta gap. which has this kind of behavior. Here I'm just drawing a stereotypical curve, the kind of curve we all sort of have in mind. At least I think we all have in mind. So at weak coupling, where the gap closes, J naught goes to 1. And then at strong coupling, it goes to 2. And in between, it's some interpolating function. In the context of n equals 4 super Yang-Mills, this J naught, which is also known as the Regge intercept, is, so this would be some function of lambda in planar n equals 4 super Yang-Mills. And much is known about it. Integrability has managed to attack this thing. There are some beautiful plots of the behavior of this as a function of lambda, even in the complex spin plane, even some papers by, I believe, Gromov and collaborators. But this is the picture. The interesting thing is that in these regimes, away from large gap, the higher spin states must conspire to give you a Regge growth which is less than 2. And exactly that phenomenon, sometimes called Reggeization, is part of what, the sort of powerful and surprising rigidity of the spectra of CFTs. In the paper in which this was rigorously proven, actually it's really the non-perturbative one which was rigorously proven in this paper by Karan Huo, he derived this Lorentzian inversion formula. And one of the implications of that formula is that CFT operators and contributions to 4-point functions, but really I guess we can think of it as local operators, live on Regge trajectories. These are analytic trajectories in spin, and that is one kind of version of spectral and OPE rigidity in CFTs, which is not definitely not immediately obvious and has made a large impact. So all those ideas together are trying to sort of unveil what the hidden structure is of CFT data. But indeed, the fact that this bound must be obeyed is a very strong constraint that we're still trying to understand.
Okay, thanks. Yeah.
Sure. There was another question.
Oh, I was asking the same. I got the answer. I was asking the reference for this non-perturbative bound, but you said it's Carnot's inversion formula.
Yeah. Analyticity and spin and conformal theories. That paper.
Okay.
And at large delta gap, this takes a form 2 minus some numerator over delta gap squared plus ... And so, yeah. There's also a nice paper by, well, there's many nice papers in this arena. I think a nice paper that gets at some of the physics of large gap, which was influential for me, is a paper by Costa Hansen and Penedonis. But there are many, and I'll put them on the document on the wiki. Also a nice paper around the same time by Kulexizi, Parnachev, and Zhiboyedov. This chaos band was used in the CFT proof of Chems by those authors I mentioned before. You can also use it to rule out CFT2s with a finite number of higher spin currents. In 2 dimensions, you can have such theories. Higher spin algebras with a finite number of currents exist, that people have studied them, but those theories, planar theories with that form, would violate the chaos bound, so you can reject them. Yeah. And they were also central in these more recent dispersive sum rules that I mentioned before. Okay, so we have about 10 minutes. Good. So to me, the question that motivated me in the wake of HPPS and Chems and all of that was, so the theory is local in AdS, great, but in what dimension is the theory local? What kind of bulk theory is it? So kind of local bulk theory is it? In other words, what are the possibilities or the constraints in the space of theories with large delta gap? And so one version of this is in what space time dimension D is the theory local. So we're familiar in top-down constructions in the context of supergravity or string theory with solutions of the form AdS D plus 1 times some compact manifold M. S5, S3, S4, S7. And in these types of simple solutions of Freund-Rubin type, LADS is of the same order as LM. And so let's call this MD minus D plus 1. So the total space-time dimension is capital D. Okay. That's the dimension in which this type of compactification is local, because it's only in that dimension that one has an Einstein gravity or supergravity approximation. So when one does a KK reduction on the internal space, you get infinite towers of light KK modes. And so in that lower dimension, the theory has an effectively infinite number of light fields of order 1 mass, or at least mass that doesn't scale with a large parameter in the game in AdS units. And there's nothing wrong with that, of course. The question is there anything wrong with the alternative, which is that you don't have this large compact manifold at all? I think that Iran is going to talk about this issue as well. I think we think about it slightly differently, so it's okay that it's coming up twice. This question sometimes goes under the name of whether you can have AdS scale separation, where you have a small m. Oops. And so I think the name is clear, right? It's a separation of scales between the internal and non-compact space. And spectrally, this is a sparseness of the light spectrum in your CFT, because remember, the spectrum of the CFT is determined by reducing all the way down to the D plus 1 dimensional AdS space. So in CFT, the question is, how sparse can my spectrum of operators that are single trace and spin less than or equal to 2 be? So if I have my vacuum here, and maybe up here, we have dimensions. So if this is a dimension plot, and here we have order C, so there are black hole states up here in this fuzzy region. And maybe here we have states of order delta gap. The question is, what happens, what's allowed to happen here? Can I have basically nothing? Indeed, the question I asked earlier, can you just have the graviton, is the extreme version of this. And I just want to emphasize, this isn't a question about whether the gap, the higher spin gap, is large. In the kind of theory we're concerned with, the higher spin gap is large. The question is just whether everything below the gap has to be populated at a certain density. And I suppose I've been harping on this question throughout the lectures, because I just think it's fascinating and open, and even in the most highly supersymmetric situation remains unanswered. One version of this question is R symmetry geometrized at the AdS scale? So I guess I'm going to write this again to show just how important I think this is. Okay. And so in the n equals 4 case, this remains unanswered. At times I've mentioned some properties of the strongly coupled spectrum of n equals 4. Let me just sort of blow through that really quickly now as a point of review. The half BPS tower consists of these operators OP, which have dimension P. They sit in a certain SU4 representation, where SU4 is the R symmetry. And these are superconformal primaries. And, whoa, sorry. And at large lambda, this is the single trace superconformal spectrum. That's it. So we don't have, first of all, things like the Konishi, which are unprotected and acquire large anomalous dimension. And we don't have other superconformal primary operators besides these. But we have all of these. And sorry, the important point here is that P is greater than or equal to 2. And the principal goes up to infinity, or at least to some scale of order delta gap, or C, where funny things happen at both of those places. So P equals 2 is a stress tensor multiplet, but you do have all these other operators in the spectrum of n equals 4 super Yang Mills. And so the question is, why do we need the P greater than 2 operators from n equals 4 superconformal symmetry alone? Could we imagine a theory where these operators are just not there? Whether we're talking about weak coupling or intermediate coupling or strong coupling. But here, in the strong coupling regime, this is the question. Must there be an S5? Could there be some UV completion of 5D maximal supergravity, maximal gauge supergravity that doesn't involve more dimensions? And so I was hoping to talk a little bit about what kind of observables we could try to use to probe this question. And I will leave open the possibility that I'll do a little of this tomorrow, although tomorrow is AdS3 CFT2 day, and I do think that deserves a full day. But I've studied a bit the idea that AdS loop amplitudes can help with this question. So let me just sort of mention briefly why. So why would an AdS loop diagram be sensitive to the extra dimensions in the first place? So we imagine some 4-point function. When we cut this diagram in the middle, everything runs in the loop. So in particular, if we ask about a 4-point function of these primaries and the stress tensor multiplet, this O2, there are couplings between O2 and other OPs, where P is greater than 2. So the 2PP 3-point coupling is non-zero. That's really just the TPP 3-point coupling related by supersymmetry, and that's non-zero by award identity. So this thing is non-zero, and so you're going to have, in computing the one loop amplitude in n equals 4, an infinite sum over P of these guys. So this amplitude knows about the extra dimensions. And indeed, if you look at its high energy behavior, you can see that capital D equals 10 just by studying this object. So the idea, which would be nice to make a reality, would be to try to constrain the structure of non-planar 4-point functions in strongly coupled theories, and ask whether bounds on those can be translated into bounds on the number of bulk dimensions. For example, if there is some lower bound on the growth in certain Lorentzian regimes of these correlators, which is sensitive to D, then you could imagine placing bounds on the number of space-time dimensions. That particular goal is just that. It's still just a goal, but there's some technology which has been developed in the past few years, which could be helpful there. And while I don't actually know if that would work, the missing ingredient is, what is the essential quote unquote bootstrap constraint on these loop amplitudes. But in combination with some of these ideas from these dispersive sum rules that others have been studying, I think that there's some possibility of ruling out this funny n equals 4 theory, and we'll see. So let me just conclude there for today. And maybe as a way to transition to Iren's lecture, she does talk about this. I guess I should have said there are some constructions in the literature in the bulk of AdS solutions that are claimed to be scale separated, and there's not consensus on whether they are totally good solutions. And the philosophy that I'm espousing today and in these lectures, and that all bootstrappers espouse, is let's try to think about this from the CFT side, where you can forget about the thorny details of what makes a good bulk solution. So that's the idea, and hopefully I've tried to convince you that in the context of classifying holographic CFTs, that idea has legs. So let me stop there.
All right. We can take a few quick questions. Jake, go ahead.
So thank you. It's a very good lecture. For this last part, for this argument you're presenting here, it looks like you're using supersymmetry very strongly as a superconformal theory as opposed to just a CFT. I mean, of course, it's possible that there aren't really any large N non-supersymmetric CFTs, but do you think supersymmetry is essential to this argument here, or it's something more general about CFT?
I don't know. So here, well, just to be clear, the logic I was trying to use, I was using supersymmetry in trying to answer this particular question about R symmetry, because I think that does seem to be a privileged type of global symmetry. So for example, CFTs can have flavor symmetries, accidental global symmetries, which are realized in the bulk by just a gauge field there. R symmetries are apparently not like that. And I don't think we really understand why. Beyond arguments of it would be weird if, we don't understand why. So yeah, here I was just trying to address that question. And we do know cases where there are boundary global symmetries that are not geometrized. But as to the larger question of whether I think the essential ingredient will be necessarily supersymmetric, I don't know if I can commit to an answer. I'm not sure. Thanks for the question.
Himanshu?
Hi. Can we show if we need an infinite tower of these OPs, or is it possible to show that a finite tower of OPs is not consistent, or
in this N=4 setting?
Yes, yeah, in the last part. Like if there is O3, then there has to be all of them. Is that?
I guess I'm trying to understand what assumptions you want to make. So certainly, yeah, you can show pretty easily that if you know that the bulk dual is an AdS5 times S5, that having a finite number of those would not reproduce the necessary behavior. And this is not something you could tell classically. So classically, by that I mean looking at a fixed number of planar correlators of light operators. Consistent truncations exist. So if you're just looking at a finite number of tree level 4-point functions of some light fields, then the light fields don't all couple to all. So you won't have the ability to see the extra dimensions, but at loop level you sort of have to. Okay, so I think if you're asking, could you rule out that possibility, assuming you need to reproduce the S5, the answer is yes.
Okay.
In the paper with Fernando Alday, we sort of showed that the behavior of these loop diagrams in a certain regime of energy encodes D. And so it sort of goes from the boundary to the bulk. Right? If someone tells you in the bulk you have some compact manifold, then you know what the asymptotic growth of states is just by looking at the dimensionality of the manifold and Weil's law for the growth of eigenvalues, remembering that the eigenvalues on S5 become the masses of the light fields in AdS. But it's the other way where we sort of established some slightly new results. And so yeah, you can show that if you don't have a sufficient density of light operators, then you can't reproduce large extra dimensions.
Okay, thanks.
Yeah.
Great. Gregory?
Yeah, I'm wondering if anything is known about the analytic structure of the melon amplitudes at loop level.
The melon amplitudes at loop level. Great. Yes. So yes, the answer is yes. And this is something that I've personally worked on. We showed how to compute bulk loop amplitudes from CFT by putting tree level data together, essentially squaring it to kind of reproduce that gluing that I drew yesterday at the end of the lecture. And from that approach, a core idea there was realizing that the melon amplitudes have to have double poles at certain, or have to have new poles at loop level. They didn't have at tree level. So in particular, let me just draw something quickly. I won't go super into detail, but let me recall from earlier. I see my notes always drift to the right during the lecture. So here, the double trace poles at tree level, we're just sitting inside these gamma functions, right? The fact that they're double poles here means that we're going to get a single power of an anomalous dimension in the cross ratio expansion. If you had a triple pole, then you would get 2 powers of the anomalous dimension, because that would give you a log squared. And so that is actually something that has to happen at the next order in 1 over C, because you can have a term in your 4-point function, which is A naught times gamma 1, the tree level anomalous dimension, squared. Right? This is order 1 over C squared. So you will have terms like this. In order to reproduce terms like this, you need a triple pole at these double trace twists. And so that means that whereas at tree level, M just had single trace poles, at loop level, it acquires a simple pole at the double trace locations too, so that altogether, the integrand has a triple pole. And not only that, but the residues of those poles are fixed, because given the tree level data, you know gamma 1. And so this actually is the essential idea for how we reconstructed loop amplitudes from tree level data. And we called it the AdS unitarity method, because it's a way to glue tree level data together to get one loop data. And you can show how to do this in the bulk and how to do this in the boundary and show that they match. So to summarize, at loop level, depending on the loop order, you will have higher and higher order poles in your melon amplitude. But it will always just be meromorphic at any fixed order in perturbation theory.
Very good, thank you.
Any more questions? No one's raised hands. So let's thank Eric again.